Welcome to third video in describing rotation series. So here is a example where we're working with. It's a simple example of a disk, rotating disk. Has a hole in the middle, and there is some pin or peg, and it's rotating about that. Well, we can look at that. We mark a at some line, imaginary line on it, to say where we started. It tells us the orientation of the disk at this time. So say this t equal to 0. You might say this is along the x-axis, and so this is at t equal to 0. And when I look at this thing, this line rotates in time. It goes counterclockwise. So this is a counterclockwise. We had noticed that it was it had gone and it was at 1 second mark. At 1 second mark, say this was rotating at speed. So angular velocity, we say angular velocity is also counterclockwise. So this is the 1 second mark. So my indicator line is in that direction at 1 second mark. Let's see, at 3 second mark, my indicator line this, but it has actually gone 1, 2, and then over here. So this is at 3 second mark. And at 1 second mark, say it is omega at 1 second mark has the value 33 pi over 18 radian per second. We're working with this example. And at 3 second mark, when I work out how fast it's going, so this is instantaneous. Angular, you might say velocity. And between here and here, it didn't start to rotate other way around. It's just rotating here this way, and it continue, and I am over here, but maybe I picked up speed. Maybe it's 44 pi over 18 radian per second. Okay, everything's clear. We want, you can see it's sped up. Used to be 33 pi over 18, it's 44 pi over 18. These numbers are just made up. Okay, I could have made 3 and 4, for instance, for easy. But we are working with this example. We just let it rip. Okay, so this crazy looking number, but this is a crazy looking number. And this change in angular velocity has happened over a time of 2 seconds. So we will say omega initially is 33 pi over 18 radian per second, and this is omega final is 44 pi over 18 radian per second, and delta t is 2 seconds, 1 second to 3 seconds. 1 second to 3 seconds. So this is an example of angular acceleration. And whatever the direction of the velocity is, angular acceleration must be in the same direction for it to speed up. So for the direction means since it's speeding up, we will use a symbol alpha for this, okay? So since speeding up, direction of alpha same as direction of omega. They must be the same direction to speed up, getting bigger and bigger, right? So, so if right here, this one is counterclockwise and this one is counterclockwise. So that means direction here is counterclockwise. The magnitude of alpha will be amount is squared divided by time. So delta omega over delta t. And I'll make sure this is positive because we're talking about magnitude, because all the direction part is in here. When we say counterclockwise, clockwise, we don't put direction part in here. So here it is a 44 pi over 18 minus 33 pi over 18 over 2 seconds, and this is radian per second. So you can see this is difference is 11, 18, 36 pi radian. And now you have a second, and second makes a second squared. So instead of meter per second squared, it is a radian per second squared. And so this is alpha in terms of magnitude. Note, for the full angular acceleration and the magnitude, we use the same symbol here. Well, if you were thinking in terms of coordinate system, you would write this in more or less a very nice way, actually. I like this way of writing because it kind of makes connection with previous things that are going on in the course, x, and this is y. These are in the plane, x and y in the plane, and this guy is 90 degrees to the disk, and this is z-axis. So you can see that, all right, omega I has a z equals to 33 pi over 18 radian per second. Instead of that, I'm going to have a plus here. Omega fz, I'm going to have a plus here, 44 pi over 18 radian per second. And so instead of clockwise counterclockwise, we will write alpha sub z is equal to the difference of this guy, omega fz minus omega iz over delta t, and that will give me 44. This is going to give me plus 11 pi over 36 radian per second squared. So right now it means nothing. There's no problem here. However, if you look at something slowing down, so let's look at another example where the disk is slowing down. So here's an example slowing down. So I have same disk. This is same situation. Maybe this is still 33 pi over 18. T equals to 1 second mark. Maybe this T equals to 3 second mark. But this time is actually 20. Let's say 21 radian per second. So clearly it's slowing down, right? The rotation is slowing down. Well, if it's slowing down, then the direction would be opposite of the way it's spinning, right? So the alpha has a direction opposite of omega. So, and magnitude will be just a difference of the two. So that will be 33 minus 21, 21 pi over 18. 33 minus 21 will be 12 over 18, 12 pi over 18 radian per second square. I'll keep it positive because this is magnitude. So this is using clockwise counterclockwise. So opposite omega is going, if I'm looking from here, is going counterclockwise. So that means alpha is clockwise. if I were to write alpha here, including both the direction and the magnitude, it will be minus 12 pi over 18 rad per second square. Alright, so that's a important note is that I can get alpha negative sometimes, because if it's spinning counterclockwise and it's slowing down, then alpha is in the opposite direction. Now if you're thinking in terms of xyz, so if I'm thinking xyz, then it's automatic almost. So I have omega iz is plus 33 pi over 18 radian per second. Omega final z equal to plus 21 over 18 pi radian over second. Then alpha z is this minus omega fz minus omega iz over delta t. So if I subtract this from here, I automatically get minus 12 pi over 18 radian per second square. So you can see that if I'm thinking in the z's, I don't have to keep track of clockwise, counterclockwise separately. Its notation brings it along all the time. Okay, so this is just in a way it's a superior algebraic tool. But either one is fine. We're probably going to use both of them. Sometimes you're going to use clockwise, counterclockwise, because really it's a lot of fun thinking in terms of clockwise, counterclockwise, and using right-hand rules and seeing if it's going this way or that way. And sometimes it's kind of too tedious to do that way, and so we just fall back on the axis. This notation sometimes is kind of help us just forget about keeping track of things that we don't need to keep track of, and we just want to get done with the algebra in a very consistent way. It's up to you. You can pick one of these and stay with that, as long as you're not making mistakes. You can see that acceleration is very tricky thing. If I am accelerating when the speed is increasing, the direction is the same as omega, so that's but if I'm slowing down, then the acceleration will be in the opposite direction and will carry a sign in my equations. It's kind of like the same thing if you thought about it's similar to like if the ball is going up and is slowing down, then the acceleration is 0.1, right? So ball going up, acceleration was pointed down, and this was negative if this direction was positive. So it's kind of similar to that, same situation. In the next video, we're going to write down some equations that we can use for situations in which acceleration is constant. Like the direction and the magnitude are same. We're looking at a duration in which the same. So the next is equations for constant accelerations, constant angular acceleration, and they will look very much like the constant linear accelerations we have used, and many people kind of remember them that way, and we're going to do some problems using that. Okay, so see you in the next video.